Awesome. Okay. So let me share my screen. Okay. Yeah. So the first thing that you're gonna see is the GitHub link that we pasted in the chat. So if you don't see it, our associates are gonna repost it for you. But basically, all you have to do is click on the link. So let me just click on the chat link that we have. So basically, you will be taken to our main GitHub, and this is going to contain the workshop. So if you do want to follow along and run everything as you go, I highly suggest it. And from there, we are just going to click open up in collab, and simple as that, basically. So today we are going to be going over the decision tree and random forest algorithms. The reason why we do them together is because majority of the time you will be using random forest instead of decision trees. But decision trees, basically, how I like to think about it is you have a bunch of features. So like, let's say you have like a fraud value. You want to determine if a transaction is fraud or not. And you have the person's gender, age, address, etc. A decision tree basically like breaks off from the start and then just keeps breaking like branches, a tree's in a branch, and it decides what feature to split all the data sets on to determine if it's fraud or not. And it just keeps going down and down. Random forest is basically a bunch of decision trees. It's going to give you like break each single tree is going to be broken up on a bunch of different features, depending on how many features you have, of course. But it's going to be broken down and you're going to get a variety of them. And random forest basically just takes like the best performing one and outputs that. So we will get more into why random forest is better in the workshop. But that is just a brief overview of what it looks like. And just check the yeah, if you have any problems, shoot a message in the chat. More than happy to help. And today we are going to be working on a data set. It's linked right over here, a mushroom data set. So again, click this link over here. You just have to scroll down past the imports, and we will be using the mushroom data set for both decision tree and random forest. So unlike the previous workshop, we don't have to download more than 2. So you're gonna move on to the Kaggle website. So for anyone who hasn't used Kaggle before, basically it's just like basically holds a bunch of data sets that you can use in any projects you want. They also have competitions, which is really cool. And then like sample code also like of a bunch of people who have done it. But to download it, we are just gonna click the download button. And wherever that is, in your folder, usually it goes into downloads. If you're Mac, Windows, I'm sorry, I don't have a Windows, so I can't really guide you to that. But usually it's going to open in the downloads folder, so you can just click Finder and navigate to downloads. And then once you have once you unzip the archive file, all you have to do is drag the mushroom CSV file. So it's gonna be, the name is mushrooms.csv, or an alternate way, if you can't drag it, is you can just click the upload file and navigate to downloads and just click that. So let's take a minute to do that. Just to make sure there's like no confusion, no questions. Okay, if there's no questions, we're gonna move along. Again, if you get stuck on something, please feel free to ask in the chat, or if you have any questions moving forward. So awesome. So today we are going to be focusing on the 2 supervised learning algorithms, which is decision tree and random forest. For anyone that has never seen algorithms before or don't know what I'm talking about, all that supervised learning algorithms means is that we have the label. We have what we want to predict. Continuing with the example of credit card fraud, the label is if the credit card transaction is fraud or not. So usually it can be seen as a 1 or 0, true or false. Usually most of the time we use numbers because the machine learning algorithm only takes numerical values. So hint, hint, most of the time we are going to have to convert those, any string values or any object variables, into numerical in order for the whole entire algorithm to work. So just to get us started, always the first step that we got to do is import any libraries that we're going to use. Usually just it's standard for any libraries that we're going to use to be at the beginning of the code. And you have it all to see. So giving a brief overview of what we're going to use, we're going to use pandas and NumPy. I highly recommend watching the data visualization and cleaning. For that, we kind of break down how to use these two libraries because this is very important. We use this for the EDA cleaning and feature engineering, which we will be going into today. Before you use the data in the algorithm, you have to ensure that it works properly and you have it clean. There's like no missing variables or anything like that. And you have the most efficient data set to use, basically. Some other libraries that we have is Seaboard and Matplotlib. So you can just copy this over here, Matplotlib. We're also going to be using Scikit-learn. Sklearn is basically just like a subset of Scikit-learn. So specifically, we're going to be using the Sklearn model selection metrics like tree ensemble. So it's just all of this. So the model selection is the train test split. This is what we're going to be using to split our data into training and testing, as well as validation, which is going to be later and I'll explain why we use it. It's just going to be later in the workshop. Then the metrics is just to determine how well did this algorithm perform. We want to know, is this algorithm actually accurate and useful for what we're going to do? So we're going to import accuracy score, position score, recall score. We're going to look at confusion matrix, and we're going to do like a confusion matrix as well. And these are some other ones you can download as well. F1 score as well is really important. It's in comparison with precision score and recall score. So another one we're going to do is decision tree and random forest, which are the classification methods that we are going to use. This one we don't really need, but this is another thing that you can import if you want to see the tree itself. We won't be doing this, but I just did want to include it if you did ever want to like copy paste it, or just to check out. And then some helper functions is also the same thing with this, just to visualize it. We won't be going over this just for time's sake. And also I'm going to be throwing a lot of information at you, so I don't want to like completely overload everyone. But if you want to check it out later on and want to play around with it, these are the libraries you can access. So right now, let's run it. And this should go without a hitch. Like there should be no issues with it. The problems where it start to occur is when, but like I asked you to import the file, is when you actually have to import the file. Because right now this is the path to the file that we will be using to the data set that we have. So I know I've said this for everyone who's attended workshops, but I'm going to go through again how to like start from the basics all the way to the machine learning model itself. But we are going to start off with understanding what is in our data set. I don't know how to stress on this enough. We have to understand what we're working with. Otherwise, we're not going to be able to take out any analysis from it. Basically, the whole point is to understand like what question are you answering for this data set? What do you want to figure out when you're using this data set? So, of course, we're going to check out the first 10 values, just kind of get a sense of what we're working with. So let's look at the data set. So let me run it to make sure everything's working. Awesome, perfect. If you're having an issue with this step, it's probably because the path itself is something's off with the path. So just double check that. But yeah, again, let us know in the chat if you're having an issue with that. So just looking at the data set, like what can anyone tell me about it? Like what kind of seems off about the data set? And you can just type in the chat. Yeah, exactly. We have letters. Like I don't know what X means. Like I don't know what W means in this sense. So the first thing we want to do is understand what in the world are these values. One way we can do this, which is the way I did it, is literally just go to Kaggle and take a look at the details. If the details themselves are like encrypted and no one can understand it, like why are we going to work with this data set? Again, everyone has to be able to understand what we are working with in order to get to the final product. So, oops, let's scroll down. So this gives us what we are working with. So what we are trying to predict is this mushroom edible or poisonous, right? Some of the features that we're going to be using is cap shape, and they give examples. So like B is bell, conical is C, convex X. And basically, instead of having strings themselves, they have just a string letter. And you can go over everything that they have over here. There's about 23. So looking over here, you can see there's 23 columns, but we'll go over how you can do that in Python itself. And yeah, so feel free to go through the features and just read through it. I'm going to give you like 30 seconds for that just so you can understand what we have going on. And it's also in the workshop if you want to take a look. Okay, 30 seconds. And yeah, so now that we have like a basic overview of what our data set is and what we're working with, you can also see when we imported the data set that there's 3 dots. Basically, all that means is just we have too many columns for it to fit. So now that we have some understanding of what's going on, let's take a look at how many observations we have and how many features we are working with. And just to do that, we do df.shape. We have about 8,000 observations we're working with and 23 features that we are working with. And since we can't see it just plainly in this data set, we can do a df.columns just to get a sense of what the columns we're working with. Of course, we did this over here, but if you want to look at it in Python, here's the code for it. And I want to see what is in these features. Like, what are we working with? Are there integers, strings, etc.? Are there float numbers? So by just looking at the data set itself, we can see that it is all letters. The letters usually mean, if we have a word or even just letters, usually that means we are working with a string or an object, which is just the type of data type we are working with. As I previously stated, the machine learning algorithm is not going to accept this. It doesn't want to work with objects. It doesn't know. It doesn't know it. That's why if you guys have ever heard of neural network, when you're using a neural network or you're trying to do like, for example, something like sentiment analysis, which is trying to understand how is this from this text, how is this person feeling? They break down that text into numbers. And there's a variety of methods to do that, which I'm not going to get into today. But if it's something that interests you, highly check it out. But for us, it's just as simple as going from like 0 to 5, for example, or 0 to 1, depending on how many numbers we have. So like, for example, like let's say veil color, we have brown, orange, white, yellow. It means we're going to have values from 0 to 3. And so before we do that, before I get into how we are going to break this down, we are still going to do some more EDA to understand what we are working with. So the next step that we are going to do is check if there's any null values. If there's any null values, we do have to address it. So usually when you're working with a big data set, for example, you can just delete that row and you don't have an issue. But if you're working with a smaller data set, for example, like ours, and there was a null value, we could remove it, but we could also we could just fill it with a 0 or use some statistical means in order to fill it. But we got lucky. There's no null values, so we don't got to worry about that. Another thing we do have to worry about is, are there any duplicate values? If there's duplicate observation, we do want to remove that because, again, like that's going to mess up the accuracy of the machine learning model. And another thing we can do to check what are we working with is to check, okay, like obviously we're predicting two classes. Okay, there's two classes. So, and let's look at veil color, for example. Yeah, we have 4 veil colors, like, and you can go step by step to ensure that you have the right amount for each feature. But for time's sake, I'm not going to go over that for now. Just take my word that it's all good. Like, this should be correct. Now, another thing I do want to check for is something called a class imbalance. Probably a very foreign word. No one's ever heard of it. You use a lot of you have to address class imbalance mainly in credit card detection. So if there's anyone here that's in finance, this is like an important concept if you're going to be working with the data set. So the way we're just going to project the class is just make a histogram plot and project the class. So the amount of poisonous and the amount of edible mushrooms we have is fairly similar, like 50-50 almost. It would become an issue if, for example, we had about like 500 poisonous values and like more than double the poisonous values, like more edible values than poisonous values. So like, for example, let's say we had a ratio of like 10% to 90%. We would have to address that because then your model isn't going to be able to predict enough poisonous values correctly. So there's a variety of statistical means in order to do this. Some of them are called upsampling, downsampling. All that means is just like double for upsampling, you're basically increasing the amount of data points that you have. And downsampling is you're reducing the amount of data, like the amount of data you have. We're lucky, we don't have to worry about that, but that is something that you do want to check for just in case that does happen. But we are lucky, we have like a 50-50 split, which means our data does have enough to train and test on. Now, before I move forward, does anyone have a question about that? I know it's like a really odd topic and like I look like I just thrown it out, but any questions so far? Because I highly recommend like asking about this if it is. It can get really complex. I'm also like still doing research on it, but it is a really important topic. So far, I don't see any questions, but if you do have a question about class imbalance, please ask, or anything that we have gone through so far. So awesome. Okay, next, the most important step I would argue is doing feature engineering. So now that we understand what we're working with, we want to adjust our features and we want to either combine them into one or we want to like break down the amount of that we actually have. So basically when you decide on features or columns to adjust or combine them, that's all that is. So let's see, just 1 second, sorry. Yeah, so feature engineer, apologies. So the next thing that we're going to be doing is decide, do we want to keep or remove anything from our data? Do we want to drop or remove something? Basically, when we're doing feature engineering, some of the reasons why we drop or remove a column is if it's like not correlated at all. We can do that using a heat map, which I'm not gonna show, but we have that in the logistic and linear regression one if you want to check it out. All you do is like a data heat map and it's fairly simple. But another reason why we might drop or remove it is that there is multicollinearity. So for example, when two features are correlated, and that can interfere with determining the value that we want or classifying the value that we want. So here is just a brief overview of multicollinearity is. I have that again in the linear and logistic regression to go over that if that is something you want to go over. Basically, all that is like, this is the statistical like formula that you want to use. And usually when we see multicollinearity above 5, that's like an indicator, okay, like we got to fix this, like this is not working. So we either have to remove those two features if they're like completely not important, just correlated with one another, or we want to adjust it or combine it. Like we can combine it together to maybe become an important variable in determining if one of our mushrooms is poisonous or edible. So another reason why we can drop or remove is like null values that can't be substituted by zero. So for example, let's say I have like a bunch of zero values in the specific features, like there's about like 10% of values for this feature. And while it might be important, there's not much that we can work with or adjust it for. So we not be able to determine the mean as efficiently as we would be able to if we had 90% of the values. So that's just another reason why. And why do we want to adjust or change columns? We want to ensure that our machine learning model is able to accurately and precisely predict exactly what we are trying to get. So we want it to classify accurately. And it also just speeds up the process. So let's say right now we're working with a small data set, but for example, let's say you are working with a huge data set, for example, that has like the data set file, for example, is like 10 gigabytes, which I know if you guys are planning to take big data class, you'll get to work with it and understand how to do that. But it takes a long time for machine learning to model to run on like a 10 gigabyte data set file. We're lucky that we just have to work with 8,000 data points, but moving forward, like if we are working with a 10 gigabyte file, it's just going to speed up the process and enhance the accuracy as well. Because again, something that we're going to see like in their decision tree right now is that it's most likely going to overfit. We want to ensure that our model can generalize onto an unknown data set. If it can't do that, then there's kind of no point in creating a model. But that is just a brief background on why we do feature engineering and how we do it. And I will show you some steps that we can take when we're doing feature engineering. Any questions so far? I just want to stop. Again, I'm going to be throwing a lot of information at you, so it's better early on to ask. Take a water break also. If not, just put like a thumbs up in the chat that you're good to go. Just want to make sure everyone's on the same page and I'm explaining it clearly to make like that everyone understands. Okay, awesome. I got like 2 thumbs up that I see. Okay, awesome. Moving along. So wait, where is it? Okay, yeah. So we'll do some feature engineering over here for the most part. But first, before we get started, I did want to break up into X and Y before we got started, just because we're going to be applying two different means to change our values from object into numerical. So the reason why we did EDA is to see, is there anything that we have to change or adjust? And obviously we came with the conclusion that yes, we do. We have strings, like we have object data sets. We cannot work with the way the data set is right now. So we have to fix that. So the first thing I did want to do is just to break up our variables into X and Y. So Y is going to be the class. The Y is what we are trying to predict, and X is all the features that we're going to use. For this exercise, we'll be using all the features, not to get like into too complex like feature engineering. But for the time being, we're just going to use all the features. But if you do want to play around with it once this workshop is done, I highly recommend like removing features and seeing what happens, or trying to combine features and seeing what happens. It would be great practice for projects moving forward, as well as if you want to do data science or data analytics. But yes, so the first thing we're going to do is this. We're going to run this, just making sure I ran everything in order. Yes, so df.drop is just dropping a class and naming all the features, obviously just giving the class. So the next thing we want to do is, again, fix the string variables. We want to ensure that our model can work. So the thing we're going to do now is something called one-hot encoding. So there's something called one-hot encoding and label encoding, which we are going to be doing. But for the X variables, we will be doing one-hot encoding. So we are just going to do pd.getDummies and take a look at what we're going to be doing. All that one-hot encoding does is just breaks all the letters and basically like orders them. So for example, let's take the veil color. That's like the first thing I saw. Again, it's just going to break it down into 0, 1, 2, 3. And that is what it's going to input into that feature, except instead of having it as object variable data type, we are going to have it as a numerical data type. So one thing to note about one-hot encoding is that it does create separate columns. So you can see here that we have over 117 columns now, which is a lot. But this is like one method that we can use. Now, obviously for the class, we don't want to do that. We can't break up the class into into 2 columns. We want to keep it the same. One way we can do that is something called label encoder. Again, it's just going to do values between 0 and 1. So is this poisonous? It's going to go 0. If this not poison, if this is poisonous, it's going to go 1. So we are going to run this over here. So we are going to do we're going to take from another library called Scikit-learn processing called label encoder and just do over here. Basically, this is just like we do with any like classifier, like any machine learning algorithm. We're going to save that as a model. We're just going to save that as an encoder, and then we're going to fit it to our data set. We're going to fit it to our feature, to the class feature. And just print out the values just to confirm that it's all good and dandy. It's 1 and 0s. Perfect. So something that can happen with label encoder that is just important to note is that it can start to overfit. So we just have to be careful of that. So for example, if we have like a multi-classification problem of over, I don't know, let's say like 10 classifications, you do have to be careful with this. But for our sake, we only have 2, so it's not going to be that big of an issue. So that's why we are going to use it. So those are just 2 methods that you can do when adjusting from a object variable to a numerical value. So now that we have our data set adjusted, we did the feature engineering, we did the EDA, we did the cleaning, we're done with our data set, we want to start making the model. The first thing that we need to do is obviously, if we, for example, let's say we didn't break up our data set into X and Y, that would be the first thing we would do. So X and Y. And then right after, we want to create our training and testing data sets. So the way we do that is X-train, we have to break it up into 4 categories. There's going to be X-train, X-test, Y-train, and Y-test. Basically, we're just breaking up the X and Y values into training and testing. So the X value is going to have a training and testing, and the Y is going to have training and testing. The way we do that is something called train test split. So we're going to input the variables X and Y, and then our testing size is how much of the data we actually want to test. So about like 30% of it goes into the testing data set, and the rest of it goes into training the actual model. Random state just randomizes how we're going to use it. You can literally put any number you want here. It doesn't really matter. You can play around with this as well. You can see. We just want to make sure that we do put random state because we want to, if we do ever want to reproduce the results that we got here, we have to ensure that we have that set to a certain number. So let's run it. Awesome. Now that we randomly split our data, it's time to actually create the model. So I'm just going to run this and we're going to go line by line. Love how this says linear regression instead of decision tree. Just going to change it real quick. But basically, first things first is we're going to create the model itself. We're going to assign it to a DT model, which is just the decision tree classifier. We are, for the time being, we're not going to play around with any parameters. I'm going to explain what that is moving forward. But for the time being, let's just set it to its default value. Next, what we're going to do is we're going to fit it. Basically, we're choosing M and B and the Y equals MX plus B. So probably all of us have heard this from like algebra is Y equals MX plus B. That is the line that we're getting basically. But M is the slope, B is the intercept, Y is dependent, X is independent. Again, if you want a little bit more in depth, we have that logistic and linear regression workshop as well. But we're just like choosing M and B. How is this going to work? So we're going to fit the model to our data set. And then the next thing we're going to do is we're going to predict the values on the test data. So like, how did the model do? We are now going to evaluate the metrics. So we have accuracy, precision score, recall score, and F1 score. I'm going to go over that in just a bit. But looking at our values, it's all one. Does anyone want to take a guess as to why this is like, what is going on? Like, what can we take away from our results? To make it a little bit more specific, can we generalize this model onto unseen data? Exactly. It's overfitting. Like there's no way that our model has 100% accuracy, has 100% precision and recall in F1. Like that is a huge red flag, and that should be a huge red flag in your mind, being like, this is definitely overfitting. We gotta fix this. So what are these metrics? What is accuracy? What is precision? What is recall? What is F1 score? Some questions I like to ask when we're gonna go through all the metrics right now, but some questions you can ask. So accuracy is out of all of the predictions we made, how many were true? So this is a link that you can take to kind of describe, like explain what everything is. It will explain it better than I can. But again, these are all just statistical measures. So basically accuracy is just taking all the true positive and negative values. So let's look at the confusion. Actually, let me explain confusion. So this is what a confusion matrix looks like. I believe it's I have it a little bit lower down as well. But a confusion matrix is just taking like, okay, out of all our predicted values, how many did we predict were true and how many were actually true? This is basically what this is telling us. This is telling us how many did I predict that were, for example, like poisonous, that were like 1, and how much of that was actually right. This is what this gives us. And then these two values is basically out of the ones that we have predicted, if it predicted 0, which is edible, but was actually poisonous, this one is going to tell us out of the ones that we predicted was poisonous, how much was it actually edible? Now, confusion matrix can get a little confusing when you're looking at them. So using a reference point like this, for example, might help a lot. So this is like true positives, true negatives, but it is a great measure to what we're going to be doing. So accuracy, you're taking the true positives and the true negatives, and you're putting it all over all of the values that you have. So basically, again, this is answering how many of these were actually true. Like out of everything we predicted, what was actually true? Precision is out of all of the positive values that we predicted, how many of them were true? So we're going to take only the true positives. So we're only going to be taking the true positives, the one that it predicted was actually it, and taking it over the true positives and the false positives. So out of the whole entire positives category, how many of it was actually true? Recall is going to be answering out of all the data points that should be predicted as true, how many did we actually correctly predict as true? This one is similar to precision, except this one is going to be taking the false negatives and true positives. Now, F1 score, it just combines recall and precision. So there's a trade-off between precision and recall. Depending on the question at hand, you might prefer one over another. So I'm just going to refer back to the credit card fraud problem, for example. So most of the time in credit card fraud, for example, let's say I am given a warning sign that my transaction was fraud, but we come to find out that this wasn't actually the case. That is okay. They made a mistake. This is basically, I want to say what, I always get precision and recall confused, but using the analogy. But let's say I don't get an alert that one of the transactions fraud and it actually ends up being fraud, right? I'd rather have the bank notify me of a fraud transaction rather than not notify me if a transaction is actually fraud. This is the trade-off between precision and recall. So if you ever do want to figure out like, which one do I want for this certain scenario? So let's take credit card fraud, for example, and let's search up like, is this precision or recall better? You can always search it up, like highly recommend or recall better. So most of the time it's probably precision in this case. So you can always like take a look at it. But we care more about like the recall value. So not precision, apologies. We care more about catching the recall. So in the credit card fraud detection case, we will want a higher recall. In our case, we will want to take a look at, how many, we don't want to eat a poisonous mushroom, right? So we want to ensure that we have, in right now, we can't really see like which one is higher or not. So for the time being, we're not going to look at, but just to note, we want to make sure that we don't classify a poisonous mushroom as non-poisonous, and then someone ends up cooking with it and dying like it's higher. It's not going to be good. So in different situations, we just do want to keep it in mind because sometimes precision is more important, sometimes recall is more important. In our case, we want to ensure that, no one eats poisonous mushroom. But here is just like a brief overview of all of it. This is what a confusion matrix looks like. And also just to note, accuracy only works for classification. So there's a variety of different statistical means for unsupervised and supervised learning, and for classification and regression. If you take a look at linear and logistical regression, you can go ahead and take a look at that. I have like a breakdown of what means you can use. But yeah, so looking at our results, we saw that it's overfitting. This isn't good. It means it's not going to generalize well onto unseen data, which is the whole point why we're creating this model. So, what can we do now to fix this classification? Can everyone hear me? I just got a connection is unstable. Okay, awesome. Just to make sure the connection is good. Sorry, I had like an unstable connection. But the next thing we want to take a look at that we can do to fix this overfitting is something called hyperparameter tuning. Basically, what we're going to be doing is we're going to be taking a look at the parameters and deciding which ones are going to be the best for our specific data to ensure it doesn't overfit. So if you have no clue what any of the parameters are, I can tell you I do not remember by heart what all the parameters for decision tree is. One thing that you could do is you can go and take a look at, all you have to do is search up like decision tree Scikit-learn, and it'll pop up this decision tree classifier. So, sorry, this is the second one. And you can take a look at all the parameters. I know this looks really scary, and you're like, oh my God, like, what in the world is this? Just take it step by step. Like read it. It's really important to read documentation because in the real world, if you are going to be working with something you haven't ever used before, reading the documentation can help you get a sense of how to use this. So some of the parameters are going to be like criterion, splitter, like max depth. So you can read it, what it is about, like what it is. If I go into every single parameter, it might take up too much time, so we're not going to do that, but I'm just going to take one example of a parameter. So like, let's say, for example, max depth. So max depth, if we are to input it to adjust the parameter, because right now it's set as none. There is no max depth. So it's going to go through all our features and create that tree. It's literally going to go through all 174 columns and split it at each node. Now, let's see. However, let's say we want to adjust it. We do not want to use all of the features because most of the time, this decision tree is going to be very, very specific to this certain data set. We want to adjust how far that tree goes down, basically, because it's going to be splitting at each single one, and it's going to be very specific to this data set. We don't want that. So let's say I want to change the max depth, right? So that is something that we can adjust in our parameters for this decision tree. Another thing that we can do is basically how it splits. So this is going to be criterion. I will go into a little bit more about how it is, what it works, but for the time being, like, just know that this is how it's going to split. So one of the things that we can do to, like, instead of going through every single parameter and inputting, you know, like Gini entropy, we can do this all at once. So something we're going to be using is something called a grid search CV. You can also use random search CV. It does basically the same thing. Basically, all it takes is the parameters that you want to test out in your classifier and test it. That's it. And it outputs exactly the best, like it's going to output the best parameters for your specific data set. So obviously, because we're not going to be going through every single parameter, testing 1, 2, 3, 4, 5, like etc. And this is how we're going to do it. So we're going to input the parameters that we want. So I personally want to play around with the criterion, the max depth, and the class weight. Criterion is we're going to be deciding between Gini and entropy. So a little bit about what Gini is. So that is the default value already. But just to give an example of like what the hell Gini impurity is, usually you will use it for decision tree and even random forest, but this is a good example of how it works. So 0 in Gini impurity means that this is the purest node possible, which is what the whole entire what all the code is looking for, what this whole entire algorithm is looking for. We want this node to be as pure as possible. What does that mean? It means that, let's take this example for example. It's going to be yes, all the values are going to be in yes. So it's going to be yes 5, no 0. This is going to be a pure node. 1, oh yeah, and here's an example of it. So it means that this node is pure. It decides like, this is it. If it's closer to 1, it means this is a really, really impure node. It means the split is literally 50-50. And you're going to get like no information from this. It's basically not going to help at all. But that is just a little bit what Gini impurity. It is a little bit complicated to understand. I can highly recommend to research. And sorry, it's going to be 0.5. So here's an example. So it's like completely split, which is 0.5. Let's see, there it is. Yeah, so I'm not going to run this right now just because it can take a long time, especially the more parameters you have, the longer it is going to take to run. That is something to note. I know one time for me, it took like over 5 hours to run it because I had over like 1 million data points. So it is important to note that this takes a really long time to run. But the one difference between grid search and random search is that random search will run faster. It just doesn't get the optimal parameters, but it gets something close to the optimal parameters. So in our case, we're going to just do grid search CV just because we do not have that many data points, not that many observations. So it's not going to take that long to run. So I'm not going to run it, but I will basically copy paste it into this new model. And all I'm doing is literally copying everything that we did over here and just pasting it just with different parameters. So when I run that, we get better accuracy score, even though it's probably not the best. It still looks like it's overfitting. But again, there's like so many parameters to play with that even it might not be the best, but this is the best for the parameters that I chose to play with. So looking at it, we can see like it has improved. It's overfitting a little bit less. So just to show you, this is another one that I was playing around with, some other parameters that I was playing around with. So I don't believe, yeah, so over here I also included random state. So again, this is just like random number, but I was just playing around with the variables just to see what would happen. And for this one, I got a accuracy of 98, precision 96, frequent 99, 98. So this looks a lot better than what we were getting before. A reason why this might be overfitting less compared to like this one, like why is this not the optimal one? If you're telling me like, oh, like this is how we're gonna do hyperparameter tuning, it's probably because I didn't include random state. But there's just a variety of factors at play here. So something I wanted to take a look at in addition to that is the confusion matrix, just to see, what is going on. Let me see how it is all doing. Accuracy, store, position, and recall. It's basically the confusion matrix. For me, it's just easier to visualize what I need rather than just getting these numbers. But this gives you like the percentage. I just want to see exactly how much of the data points are accurate, how many of them like aren't predicting. So just to understand this confusion matrix, so basically this is the predicted values. So let's say we predicted that this is edible. And it actually is edible. It's about 1,234 data points. Now, let's say we predicted that this is poisonous and was actually poisonous. It was about 1,164 points. Now, looking at these two numbers, let's say that the model predicted that this was edible, but it turned out that it was actually poisonous. This is what we want to avoid as much as possible. And by our like model, we were able to minimize that. However, the trade-off is that now we predict that even if it is poisonous, we basically have false positives. So basically that we predicted it was poisonous, but it wasn't actually. We'd rather have this than we would if we predicted it wasn't poison, it actually turned out to be poisonous. So looking at confusion matrix, this is great. However, like we do have in the back of our mind that, it still looks like it's overfitting. So decision trees tend to be prone to overfitting, and that's why we do random forest, because it is using like a bunch of decision trees and putting it into one. So random forest reduces overfitting for most of the time. Any questions before I move forward about decision trees? And the validation, just to mention, the validation set we're going to be working with a bit later, but that's another step to see like how it's doing. Basically, it's another testing data set. But any questions about decision trees? Because now we're going to move on to random forest. Any questions at all? Please ask. Okay. If not, please just message the associates. More than happy to help you out. Okay, if no questions, we will be moving forward to lo and behold, random forest. So, 1 second, sorry. Okay, so again, I'm just gonna do the same thing just for the sake of seeing it, so you guys know this is the next step to do. Now that we have that slide, trying to split, let's see how it does on a regular model. So let's remove this. Let's just run it on a regular model. We can see obviously it's overfitting. 100%, we're seeing 100% again. Again, indicator, it's overfitting. I just put this parameter here just to see oh, is it gonna adjust it? And it definitely did. So you can see just based off the numbers we got over here, from just inputting only one parameter, it's a lot better than we saw over here, for example. But moving forward, again, I want to understand what are the parameters in random forest. So again, you can just search up random forest scikit-learn, from this library, and this is going to give you all of the parameters that we have. So again, you'll see some familiar ones because decision tree and random forest are so similar. We have criterion, max depth, split, yada yada. So yeah, and you even have impurity here. But again, feel free to go through it and understand it. I'm going to tell you, I don't remember off the top of my head every single parameter. It's easy just to search it up and understand what parameters I do want to adjust. And you can read which each one is. Again, important to understand documentation and be able to know how to read documentation. But moving forward, again, this is the model I just had previously. So we're going to do like max of 3. And you saw like it improved. But I don't want to go through every single number in that step. I just want to be able to do a grid search, and I just want to tune my parameters, these specific parameters, using these like two. For example, I only want to do test Ginny and entropy, and I only want to test these max depths and this class weight. Class weight is just class imbalance. Is asking is there a class imbalance or not, and do we have to adjust for it? So let's run it. This one, just to show you how long it runs, it's going to take a long time to run. But in the meantime, while it runs, so like let's say it output, for example, max step 3, we run it and you can see like if it doesn't, it goes a lot better. So like over here, for example. But yes, so let's run this. Let's run the parameters it gave us that were the best parameters for this specific model. Let's just copy paste it. Literally all you have to do is copy paste it. And let's run it and see what happens. We can see that we get a solid accuracy score of 99, recall of 98, F1 of 99, precision again 100%. And we can rerun this one as well. So all you would have to do if you do want to see it and rerun it is you can do just RT pred, RF pred, sorry. Because we want the random forest values, not this. But yeah. And another thing we can do to also check for, if it's overfitting or not, is we can do a validation set. So again, as I said before, it's almost like a testing. It's like a second, I think, set to ensure that our data can generalize to new data. So basically, all you have to do that we have X and Y, X and Y, we have X train, Y train, all of that. We already have this step done. Let me see it. There it is. Now that we have this step done, this would just be the additional one that we can do. So we would break up our X train and Y train into X train and X val, which is the validation set. Test size and random state are all the same. And then we will run it. I want to do it on max depth, for example. And we are going to run the model again, do everything we did over here, and output the accuracy and precision. So we can see on our validation set that it is actually true what it says over here. Like it is fitting. It is doing well. The score is like a line. So we can see like accuracy 98, precision 100, recall 97, and F1 is 98, which is really similar to the values we got here, which means it's all set. It's doing good on generalizing to unseen data. Okay, now that is just a brief overview of decision trees and random forests, but more topics that you can explore for decision trees and understanding like all the statistical measures, because there are a bunch. Today, I didn't want to throw everything at you and expect you to like learn every single one because there are so many. I just wanted to give you a brief overview of like how everything works, how can you code it out, and what measures can you do. But some other topics that you can explore for decision trees and random forests, because again, random forest decision trees are very similar. You can explore pruning, information gain, entropy, card, Gini index. Like there's just like a bunch of specific measures, and most of them are for the parameters themselves. So as I talked about, like Gini, for example, is the impurity. Like this is the one we mainly use a lot, or I mainly use a lot, is the Gini impurity. But again, there are a bunch of other ones. There's also, for example, entropy. Entropy is mainly for associated with information gain. So depending on looking at this example that we had over here, depending on this, when we break up this specific node on age, how much information can we gain from this? So let's say that we have 4 yeses and 0 no's. This means we are gaining, like we have a high information gain because this is separating this separates the values the most basically. We can understand that from breaking age up into these 3 categories, that middle age as that we will see that if it's middle age, that then the classification is going to be yes. And that has a higher information gain, and that's what we want. That is just like one example of entropy. And then there's another one called log loss, which is similar as well to entropy. But again, it's just another statistical measure, which again, I might not be the best person to explain it, but feel free to read it over here. It's literally cross entropy loss. I use this in neural networks, but another thing you can read about, would not be the best person to explain it. It's going down, sorry everyone. But yeah, this is like the criterion that we split on, which was the entropy, like an information gain, or the Gini index, like those are the 2 ones. And over here, you can just read about what entropy is and what Gini index is. Hopefully I explained it a little better instead of in words during the workshop. But that concludes our workshop for today. I know it was fairly fast, only an hour, but thank you everyone. Does anyone have any questions? I know I threw a lot at you, but is there any questions that you have about decision trees, random forest, anything that I explained that I didn't do effectively? At the bottom of the workshop is a feedback form, which I'm going to attach in the chat right now. If you could please fill it out and let me know what you guys thought, please do. It's important to me that, moving forward, the workshops I make are informative and I explain it thoroughly so everyone can understand it. Because I know when I was learning this, like, I was just like, oh, I do not know what's going on. But hopefully you guys enjoyed. And please, any questions, message in the chat right now, or feel free to reach us out in Discord or even my LinkedIn. Again, any questions, I'm happy to answer. I love to talk about this topic, so please feel free. And please fill out the feedback form just so I can get an understanding of how I can improve the workshops moving forward. But other than that, if there are no questions or comments, and once everyone filled out the feedback form, I'm gonna stay for like 5 more minutes. You guys are free to go. And that is the end of the workshop. I hope everyone enjoyed. I appreciate you taking time out of your day to come and listen to me spiel about decision trees and random forests. So thank you, everyone. I hope everyone has a great day. I'm gonna stop sharing and stop the recording.